Welcome back. How was the night when Oklahoma reached 29 degrees Celsius during a thunderstorm? Midnight. The sky over Oklahoma is flashing with lightning. Rain is falling. Thunder is rolling across the plains. And the temperature is rising. Not slowly, not gradually. It jumps from the low 70s to 84 degrees Fahrenheit. At midnight, during a thunderstorm, people step outside expecting relief from the rain. Instead, they feel desert wind. Hot, dry, suffocating. It makes no sense. Storms are supposed to cool the air. That's the rule. But on May 29, 2000, a collapsing supercell over Oklahoma broke that rule completely. This wasn't faulty equipment. It wasn't a data glitch. It was a rare atmospheric phenomenon called a heat burst. And this one was so extreme, it stunned meteorologists across the country. The storm didn't just flash lightning. It rewrote the temperature at midnight. Oklahoma is unstable, but not unusual. It's late spring, peak severe weather season. Warm air from the Gulf of Mexico is streaming north. Dry air from the high plains is sliding east. And above it all, a strong upper-level jet stream is slicing across the sky. The ingredients are textbook: moisture, instability, wind shear. By 5 p.m., thunderstorms begin firing west of Oklahoma City. Classic supercells. Tall, rotating, electrified. They produce heavy rain, lightning, even brief hail. Nothing extreme, nothing historic. Just another stormy evening on the plains. But high above the ground, nearly 20,000 feet up, something different is happening. The air there is incredibly dry. Bone dry. The kind of dryness that drinks moisture instantly. And as the storms begin to weaken after sunset, their rain cores start falling through that dry layer. That's when the shift begins. Because when rain falls into extremely dry air, it evaporates. And evaporation absorbs heat, which cools the air dramatically. That cooled air becomes dense, heavy. It starts sinking. Meteorologists call it downdraft. At first, it's subtle, invisible to anyone on the ground, but it's accelerating. The more rain that evaporates, the colder and heavier the air becomes. And the heavier it becomes, the faster it falls. The storm above is beginning to collapse inward. Updrafts weaken. Lightning spreads wider but grows less frequent. The towering cloud slowly loses its structure. Radar operators notice reflectivity cores shrinking. Echo tops begin lowering. The supercell is dying, but its energy isn't gone. It's changing form. And collapse, in meteorology, can be violent because all that cooled air, all that stored energy, has only one direction left to go. Down, fast, and toward the sleeping towns below, waiting, silent and unseen in darkness. Tonight, suddenly, the thunderstorms are weakening. Lightning becomes scattered. Rainfall lightens. Most people assume the worst is over. But high above the plains, the downdraft is now fully formed. Cold air is plunging toward the ground at incredible speed. Not drifting, falling. As it descends, something critical begins to change. Because air doesn't just fall, it compresses. And when air compresses, it heats up. The same principle that makes a bicycle pump grow warm in your hand. Pressure increases. Temperature rises. The pocket of cooled air that began its journey miles above the surface is now racing downward. And as it falls into denser layers of the atmosphere, it's being squeezed tighter and tighter. The evaporation that once cooled it has stopped. Now the process reverses. Compression replaces cooling, and the air begins to warm rapidly. Meteorologists later calculate the descent rate. Thousands of feet per minute, like an invisible elevator shaft collapsing from the sky. By the time the downdraft reaches the lower atmosphere, it is no longer cold. It's hot, but the ground hasn't felt it yet. At the surface, residents of central Oklahoma are still watching distant lightning, still hearing faint rumbles. still expecting cool, rain-cooled air to drift in. Instead, the collapsing storm is about to deliver something else entirely. A concentrated column of descending air, superheated by compression, bone dry from evaporation, and accelerating straight toward the surface. The pressure inside that column continues building. Momentum stacks on momentum. The faster it falls, the hotter it becomes. There's no warning for this. No siren. No advisory. Because radar doesn't show temperature. And nobody expects a thunderstorm to raise the heat after dark. But the collapse is nearly complete. Seconds away from impact. And gravity is about to finish the job below. Tonight's suddenly here. It hits without rain. A violent gust tears across central Oklahoma. Trees bend. Loose patio furniture skids across concrete. Wind chimes scream in the dark. And the temperature surges. Weather stations begin reporting it almost simultaneously. 73 degrees. 76, 79, 82, 84 in less than 30 minutes. During a thunderstorm, the air feels wrong. Not humid, not storm-cooled, dry. Relative humidity plummets. From comfortable evening levels to desert conditions in minutes. Lips crack, eyes sting, breathing feels sharp. The downdraft has reached the surface. When the superheated air column slams into the ground, it spreads outward violently. Meteorologists call it an outflow boundary. But this isn't a cool outflow. It's a blast furnace. Wind speeds spike over 50 miles per hour. Some stations report gusts above 60. Power lines sway. Dust lifts from fields even as lightning flickers overhead. Thermometers in Oklahoma City, Chickasha, El Reno, Norman, and Yukon confirm the spike. This isn't one faulty sensor. It's regional. Emergency managers begin receiving confused calls. Is there a fire nearby? Why is it so hot? Windows are opened for relief, then slammed shut against the wind. The descending air, compressed and heated during its fall, has reached the surface fully transformed. What began as evaporatively cooled air miles above has reversed into superheated, bone-dry wind. The pressure surge is measurable. Barometers jump. The air slams outward in all directions, flattening grass and rattling windows. Fire danger spikes instantly. Dry grass crackles. Small embers from lightning strikes suddenly matter. Meteorologists later calculate temperature jumps of more than 15 degrees in some neighborhoods. One rural station reports a peak gust near 65 miles per hour. Another logs humidity below 20%. The temperature doesn't just climb. It peaks, 84 degrees, at night, with lightning in the sky. And just as quickly as it arrives, the heat begins to ease. Within an hour, temperatures start falling again. The burst moves east, spreading and weakening. But for those 40 minutes, the laws of expectation were shattered because a thunderstorm made the night hotter than the day. And no one watching the lightning understood yet that they had just witnessed one of the most extreme heat bursts ever recorded in American weather history. Historic, rare, unforgettable, and scientifically extraordinary. Documented. A heat burst is born inside a dying thunderstorm. When the storm's updraft collapses, rain falls into extremely dry air high above the ground. That rain evaporates. Evaporation cools the surrounding air dramatically. The air becomes dense, heavy, and gravity pulls it downward. At first, the descending air is cold, colder than the surface. But as it falls through thousands of feet of atmosphere, pressure increases. And increasing pressure means compression. Compression means heat. The physics is simple. The effect is not. Imagine dropping a block of air from nearly 4 miles above the ground. As it falls, it is squeezed tighter and tighter. Every 1,000 feet adds pressure. Every bit of pressure adds temperature. By the time it nears the surface, the original cooling effect has been completely reversed. The air is now warmer than it was before it ever fell. Drier too, because all the moisture that once existed inside that storm core evaporated on the way down. What reaches the ground is a column of superheated, bone-dry air, accelerating outward like a shockwave. Meteorologists measure these bursts by their sudden temperature spikes, dramatic humidity crashes, and intense straight-line winds. They are rare. Most storms never produce one. Even when they do, the warming is often modest. 5 degrees, maybe 10. But May 29th, 2000 was different. The dryness aloft was extreme. The downdraft was deep. The compression was efficient. Everything aligned. The collapsing supercell essentially turned into a giant atmospheric piston, slamming heated air toward the surface. The result? A midnight temperature spike strong enough to rival afternoon highs. And because heat bursts are localized and short-lived, they can vanish almost as quickly as they appear. No lingering cloud signature. No rotating wall cloud. No funnel. Just physics. Rapid. Invisible. And violent. A storm that cooled itself first, so it could heat the ground later. Scientists later reviewed balloon soundings from that evening. They showed a pronounced dry layer between 10,000 and 20,000 feet, exactly where the evaporating rain would have fallen. That dry layer acted like fuel. The deeper it was, the longer the air could fall and compress, and the stronger the heating became. Heat bursts are not magic. They are thermodynamics in motion. But when those equations unfold over a sleeping city at midnight, they feel supernatural. When the descending column struck the surface, it didn't stop. It spread outward in all directions. Meteorologists call this a downburst. But this one carried heat instead of cold. Wind gusts ripped across central Oklahoma, toppling small trees, snapping weak branches, and sending trash bins tumbling down empty streets. The air was so dry that sweat evaporated instantly. Skin cooled and burned at the same time. Some residents later described it as opening an oven while standing inside a wind tunnel. Power flickered in some neighborhoods. Dust devils briefly formed along rural roads. Loose soil lifted despite the earlier rainfall. It wasn't a tornado. There was no rotation, just straight-line force. At several monitoring stations, wind gusts exceeded 60 miles per hour. Combined with humidity below 20%, the environment briefly resembled the edge of a wildfire zone. Lightning still flashed in the distance, but now the rain had mostly ended. The storm above was dissipating, its structure collapsing into scattered clouds. What remained at the surface was energy. The burst expanded outward, covering dozens of miles in less than an hour. As it spread, its intensity slowly weakened. Temperatures gradually fell back into the 70s. Humidity began recovering. The oven door closed, but the memory lingered. Because heat bursts don't look dramatic. There's no funnel cloud, no rotating wall, just invisible air descending at high speed, rewriting the conditions at ground level. Weather observers watching live data streams saw the anomaly unfold in real time. Temperature lines spiking upward, humidity lines plunging, wind barbs flaring outward across the map. Some stations recorded pressure jumps of several millibars in minutes. That pressure surge helped drive the hour blast. The sensation passed quickly, but its footprint on the data was unmistakable. For residents, it was confusion, a storm that ended with heat instead of relief. And by midnight's end, the sky above Oklahoma had mostly cleared, leaving behind calm air that felt almost normal again. Almost. Its strength was short-lived, but its precision was extraordinary. A narrow window, a sharp spike, then retreat. Measured and undeniable. Real. 911 centers receive scattered calls. Is there a fire nearby? Why is it suddenly so hot? Some residents reported smelling smoke, even though there was none. Air conditioners kicked on unexpectedly. Windows that had been opened for cool night air were slammed shut against the blast. Farmers stepped onto porches expecting rain. Instead, they felt desert wind across wet soil. The ground steamed in places where earlier showers had fallen. Meteorologists monitoring local stations watched the data in disbelief. Temperatures climbing, humidity collapsing, wind gusts flaring outward from a weakening storm. At first, some questioned the sensors. Faulty readings happened, but when station after station confirmed the same spike, the pattern became undeniable. This wasn't equipment failure. It was atmospheric. In a region used to tornado sirens and hailstorms, this felt different. No warning, no visible threat, just invisible heat in the dark. By the time most people understood that something rare had just happened, the air was already cooling again, and the storm, which had seemed so powerful hours earlier, was gone. A brief event, but deeply unsettling, memorable, strange. So yeah, by the next morning, the atmosphere had reset. Temperatures returned to normal. Humidity stabilized. The sky cleared as if nothing unusual had happened. But the data told a different story. Meteorologists across Oklahoma began compiling reports. Weather stations from Oklahoma City to surrounding rural towns had captured the same signature: a sharp temperature spike, a dramatic humidity crash, and powerful straight-line winds, occurring during the weakening phase of a thunderstorm. The event quickly drew national attention. Heat bursts are rare. Documented cases exist in Texas, Kansas, and other plain states. But few have been this strong. Fewer still have pushed temperatures into the mid-80s at midnight. Researchers reviewed radar archives. They studied upper air soundings. They analyzed pressure trends and wind patterns. Everything pointed to a textbook heat burst, only amplified. The dry layer aloft had been unusually deep. The downdraft unusually strong. The compression unusually efficient. It was a perfect alignment of atmospheric ingredients. In the years since, the May 29, 2000 heat burst has been cited in meteorology courses as one of the clearest modern examples of the phenomenon. Not because it caused destruction, but because it revealed something powerful. A storm does not end quietly. Sometimes its final act is its most dramatic. That night in Oklahoma, a collapsing supercell turned gravity and thermodynamics into spectacle. No sirens, no headlines the next day, just a spike on a graph, a memory in the dark, and proof that even familiar storms can still surprise the people who live beneath them. Heat bursts remain difficult to predict, but when the balance is right, the atmosphere flips its script. Cooling becomes heating. Night becomes summer. That is what made May 29th unforgettable. For 40 minutes, Oklahoma experienced something that felt impossible. A storm that made the dark hotter. Briefly. Exactly. Subscribe for more histories